This video is Module 11, IPv4 addressing for the Cisco Netacad Introduction to Networks course. In this video, we're going to be looking at IPv4 address structure, IPv4 unicast, broadcast, and multicast, the different types of IPv4 addresses, network segmentation, and subnetting an IPv4 network. We will also be looking at subnetting a /16 and a /8 prefix, subnetting to meet requirements, variable length subnet masking or VLSM, and structured design. First, let's take a look at IPv4 address structure. An IPv4 address is a 32-bit address that is made up of a network portion and a host portion. When determining the network portion versus the host portion, you must look at the 32-bit stream. A subnet mask is used to determine the network and the host portions. So when we look at this, the left side is the network portion and the right side is the host portion. To identify the network and host portions of an IPv4 address, the subnet mask is compared to the IPv4 address bit for bit from left to right. The actual process used to identify the network and hosting portion is called ANDing. A-N-D-I-N-G, ANDing. A prefix length is a less cumbersome method used to identify a subnet mask address. The prefix length is the subnet of bits set to 1 in the subnet mask. It is written in a slash notation. Therefore, we can count the number of bits in the subnet mask and prepend it with a slash. A logical and Boolean operation is used to determining the network address. Logical AND is the comparison of two bits where only one and 1 produces a 1, and any other combination results in a 0. So 1 and 1 equals 1, 0 and 1 equals 0, 1 and 0 equals 0, and 0 and 0 equals 0. So 1 equals true and 0 equals false. To identify the network address, the host IPv4 address is logically ANDed bit by bit with the subnet mask to identify the network address. Within each network, there are 3 types of IP addresses: the network address, the host address, and the broadcast address. Now let's take a look at unicast, broadcast, and multicast. The unicast transmission is sending a packet to one destination IP address. That's at uni or 1. So for example, the PC at 172.16.4.1 sends a unicast packet to the printer at 172.16.4.253. So 1 to 1. In a broadcast transmission, the packet is sent to all other destination IP addresses. For example, the 172.16.4.1 PC sends a broadcast packet to all other IPv4 hosts. With a multicast transmission, it's sending a packet to a multicast address group, not all addresses, but a multicast. So for example, the PC 172.16.4.1 sends a multicast packet to a multicast group address, so not all of them, but a multicast. Next, we're going to look at the types of IPv4 addresses. When we look at the RFC 1918, public IPv4 addresses are globally routed between Internet Service Provider routers, or ISP routers. Private addresses are common blocks of addresses used by most organizations to assign IPv4 addresses to internal hosts. And private IPv4 addresses are not unique, and they can be used internally within any network. However, private addresses are not globally routable. If we're going to route to the internet, we need to do Network Address Translation, or NAT. That translates private IPv4 addresses to public IPv4 addresses. NAT is typically enabled on the edge router, or gateway router, connecting to the internet. It translates the internal private addresses to a public global IP address. We also have special use IPv4 addresses. We have the loopback address, that's 127.0.0.0/8, commonly identified as 127.0.0.1. It's used on a host to test if the TCP IP is operational. We also have linked local addresses. They are commonly known as automatic private IP addressing, or APIPA, APIPA. They are self-assigned addresses. It's used by Windows DHCP clients to self-configure when no DHCP servers are available. We have legacy classful addressing, RFC 790. It allocates IPv4 addresses in classes, class A, B, C, D, and E. Classful addressing wasted a lot of IPv4 addresses, and it's really not used anymore. However, it is helpful to understand classful addressing and know how it's broken down. IP addresses are assigned by the Internet Assigned Numbers Authority, or IANA. They manage and allocate blocks of IPv4 and IPv6 addresses to 5 regional Internet registries, or RIRs. The RIRs are responsible for allocating IP addresses to the ISPs, who provide v4 addresses blocks to smaller ISPs and organizations. Next, we're going to take a look at network segmentation. Segmentation is when we break down the network into smaller bits. So many protocols use broadcast or multicast. ARP uses broadcast to locate to other devices. Host send DHCP discover broadcast to locate a DHCP server. And switches propagate broadcast out on all interfaces except the interface on which it was received. So the only device that stops broadcast is a router, and routers do not propagate broadcast. Each router interface connects to a broadcast domain, and broadcasts are only propagated within that specific broadcast domain. Now, there can be a problem with large broadcast domains. That is that hosts can generate excessive broadcast and they negatively affect the network. The solution is to reduce the size of the network to create smaller broadcast domains in a process called subnetting. So we divide the network address 172.16.0.0/16 into 2 subnets of 200 users each, 172.16.0.0/24 and 172.16.1.0/24, and the broadcasts are only propagated within those smaller broadcast domains. Subnetting reduces overall network traffic, and it does improve network performance. It can only be used to implement security policies between subnets, and subnetting reduces the number of devices affected by abnormal broadcast traffic. And subnets are used for a variety of reasons, including locations have different subnets. A group or function, you might break your subnet down by functions. So admin might have one subnet, HR would have another, accounting and students would all be broken into separate subnets. Or you could break it into device types as well. Subnet and an IPv4 network. When we break down subnets on an octet boundary, networks are most easily subnetted at the octet boundary of /8, /16, and /24. And you notice that we're using longer prefix links. It decreases the number of hosts per subnet. So when we subnet an IPv4 network, networks are most easily subnetted at the octet boundary of /8, /16, and /24. And we notice that using a longer prefix links decreases the number of hosts per subnet. In the first table, we have 10.0.0.0/8. It's subnetted using a /16. And in the second table, we use a /24. And I'm going to pause the video here for a second so you can look at each one of these tables. On this table, we see 6 ways to subnet a /24 network. And I will say at this point that I do have a series of videos on my channel on subnetting and advanced subnetting. And if you check my channel and look at the playlist, you'll be able to find those. Now, when we subnet a /16 and a /8 prefix, this table will give us an example of doing these. It highlights all the possible scenarios for subnetting a /16 prefix. Now, if we think about a large enterprise that requires at least 100 subnets and has chosen the private address of 172.16.0.0/16, that's its internal network address. And the figure on the right displays the number of subnets that can be created when borrowing bits from the 3rd octet and the 4th octet. And notice how there are now up to 14 host bits that can be borrowed, and at least 2 bits cannot be borrowed. And to satisfy the requirements of 100 subnets for the enterprise, 7 bits, 2 to the 7th power equals 128 subnets, and that would need to be borrowed for a total of 128 subnets. Now, if we think about a small ISP that requires 1,000 subnets for its clients using a network address, we would use 10.0.0.0/8, which means there are 8 bits in the network portion and 24 host bits available to borrow towards subnetting. And the figure on the right displays the number of subnets that can be created when borrowing bits from the second and third octet. And then we have up to 22 host bits that can be borrowed, and the last 2 bits cannot be borrowed. And so to satisfy the requirement of 1,000 subnets for the enterprise, that's 10 bits, 2 to the 10th power equals 1,024 subnets, and that would need to be borrowed for a total of 128 subnets. Next, let's take a look at subnetting to meet requirements. So an enterprise network will have an intranet, a company's internal network, typically using a private IPv4 address. And then we have a demilitarized zone, or DMZ, a company's internet-facing servers. So we have the external and the internal. So we have our internet here, we have our DMZ, and then we have our internal intranet. So a company could use 10.0.0.0/8 and subnet on the 16 or 24 network boundary, and the DMZ devices would have to be configured with public IP addresses. And there are 2 considerations when planning subnets: the number of host addresses required for each network, how many hosts do we need for each subnet, and then the number of individual subnets needed. So how many subnets are we going to need? If we need 8 subnets, that's going to give us 30 hosts per subnet. In this example on the right here, the corporate headquarters has been allocated a public network address. It has 10 host bits by its ISP, providing 1,022 host addresses. There are 5 sites, and therefore we need 5 internet connections, which means the organization requires 10 subnets, with the largest subnet requiring 40 addresses. It allocates 10 subnets with a /26 subnet mask. Now we're going to take a look at VLSM, or variable length subnet masking. And given the topology, 7 subnets are required. In other words, 4 LANs and 3 WAN links. And the largest number of hosts is in building D with 28 hosts. So a /27 mask would provide 8 subnets of 30 host IP addresses and therefore support that topology. However, the point-to-point WAN links only require 2 addresses and therefore waste 28 addresses for each of the total 84 unused addresses. So it's a waste of IP addresses, or host IP addresses. So we don't use the traditional subnetting scheme because it's not very efficient. So VLSM was developed to avoid wasting addresses by enabling us to subnet a subnet. The left side displays the traditional subnetting scheme here, and the one on the right shows a variable length subnet mask that we can break down those IP addresses or those subnets into smaller chunks, and we don't waste as many host addresses. The resulting topology with the VLSM applied is much more efficient. And I will say here that I do have videos on VLSM as well. If you check my channel, you'll be able to find those. So using the VLSM subnets, the LAN and inter-router networks can be addressed without unnecessary waste, as shown in the logical topology diagram below. Last, we're going to take a look at structured design. IP network planning is crucial to develop a scalable solution for an enterprise network. So to develop an IPv4 network-wide addressing scheme, you need to know how many subnets are needed, how many hosts a particular subnet requires, and what devices are part of the subnet. And that which parts of the network use private addresses and which ones are going to be using public addressing, and how many others are determined in your factors. So we examine the needs of an organization's network use, and we look at how many subnets will be structured. We perform a network requirement study by looking at the entire network to determine how each area will be segmented. We also determine how many subnets are going to be needed and how many hosts per subnet. We determine DHCP address pools and the layer 2 VLAN pools as well. And then last, within the network, there are different types of devices that require addresses. We have end user clients. Most of those we can use DHCP to reduce errors and burden on the network support staff. V6 clients can be obtained using DHCP V6 or Slack. We have servers and peripherals. We have servers that are accessible from the internet or forward-facing servers, and they must have a public IPv4 address, most often using NAT. We have intermediary devices, and those devices are assigned addresses for network management, monitoring, and security, and we have our gateway. And when developing an IP addressing scheme, it's generally recommended that you have a set pattern of how addresses are allocated to each type of device. So what did we learn in this module? We learned about IP addressing structure. We learned about IPv4 packets. They can be unicast, broadcast, and multicast. We learned about who assigns IP addressing, that reducing large broadcast domains using subnets creates smaller broadcast domains and reduces overall traffic. We also learned about IPv4 subnets and using one or more host bits as a network bits. However, networks are most easily subnetted at the octet boundary of 8, 16, and 24. And we learned about VLSM and how it allows network space to be divided into unequal parts, which is more efficient. These are the new terms we learned in this module. I'm going to leave the screen up for a few seconds for you. Thank you for watching the video. Thank you for sharing, and I hope you have a great day.